Okay, now we're working on the section 7.6 radical and exponential equations. So this is an important difference for you to see, is that we're talking about equations now. Okay, this is our, this is the opener, right? Remember that 72 is 9 times 8. 9 is a square. 8 is 4 times 2. So 36 times 2. So what we had then, this becomes the square root of 36 times the square root of 2. Square root of 36 is, of course, 6, which gives us 6 root 2. This one we have to use our conjugate. Okay, so we're going to multiply over 2 plus root 3. We're going to multiply this by the conjugate. This is what we... Apologies. Last class. I'm sorry that this is giving me such trouble. Root 3 and 2 minus root 3. Okay, so when I multiply across, I get 2 minus root 3 over difference of squares, so it's going to be 2 squared, which is 4, minus root 3 squared is 3. 4 minus 3 is 1, so 2 minus root 3 over 1 is just 2 minus root 3. All right, on our next one, we actually did this as an example in the last class. I'm going to take the cube root of 8, and then I'm going to square it. I do this because I know that the cube root of 8 is 2. So that's 2 squared, which is 4. So that's my answer. All right, moving on to the next. To do last. Next slide. Okay. Equations containing radicals as coefficients or constants are solved by applying previously studied methods, the things we've already learned how to do. So, what we're going to do here, notice here's some examples, right? Here it is as a constant, and here it's a coefficient. All of these we've learned how to solve. This one, it's a constant. Okay, so all of these we've learned how to solve already. These are not the ones we're working on today. These are not equations. Okay, now what we want is if the variable is inside the radicand. See, notice the 4 is inside the square root symbol. So a radical equation, this is on your formula sheet. A radical equation is an equation that contains a variable in or inside the radicand, or has a variable with a rational exponent. So either it's going to be something like the cube root of y, or it's going to be y to the 2/3, something like that. Okay, so to solve a radical equation, first we isolate the radical containing the variable. Okay, so that's what we've done. Here we would subtract 4 from both sides. I didn't really mean to draw that line. Okay, 4 from both sides. And that would give us, our radical is now isolated. Okay. Next, whoops, I didn't mean to be red, I meant to be white. There we go. Eliminate the radical by raising both sides of the equation to the appropriate power. And that's going to be whatever the index is. If this was a cube root, I'd cube it. If this was a 4th root, I'd raise it to the 4th. Okay? So in this case, it's a square root, so I raise it to the 2. And that eliminates the square root, and I end up with 4x. Now that's 4 squared, so it is plus or minus 4. Okay, so all right, squaring both sides of an equation may introduce an extraneous solution. Therefore, all solutions must be checked. These are things to watch out for. You must check it. Notice when we check the positive one, it works. But when we use the negative, I end up with an imaginary number. So the negative does not work. That's an extraneous solution. All right, example 2, solve. All right, so the first thing we said, isolate the radical. So I add the 2, and I'm going to divide by 3. And that gives me the 4. Next, I square both sides. So I square both sides, and I have radical x plus 4 squared gives me x plus 4. 4 squared is 16. Subtract 4 from both sides, I get x equals 12. Now I got to check it. Okay, so I go back to the original equation, not one of the intermediate equations. I plug in the x of 12. 12 plus 4 is 16. Square root of 16, of course, is 4. So now I have 3 times 4 minus 2. Well, that's 12 minus 2 is indeed 10. So that checks. All right. Now, isolate the variable that has the rational exponent. So we're going to subtract 5 from both sides. And that leaves us with x to the 1/4 equals negative 2. So what I have to do is take both sides and raise them to the power of 4, which is going to turn that 1/4 into a 1. So I raise both sides to the power of 4. Negative 2 to the 4th is 16. So now I plug that back into the original equation. I need to know if 16 to the 1/4 plus 5 is equal to 3, right? I need to know that. Well, 16 to the 1/4 is 2. 4th root of 16 is 2. 2 plus 5 is 7. That is not 3. Therefore, there are no solutions because this would go as an erroneous or extraneous solution. All right, there is a distinction between an equation containing radicals and a radical equation. There is also a distinction between an equation containing an exponential expression and an exponential equation. Okay, an exponential equation is an equation in which a variable occurs in an exponent. So we're saying that it would be x, not x. We're saying it's going to be 2 to the x equals, let's not do that, equals 8. Okay, that's an exponential equation. I have an x in the exponent. Okay, so property of equality for exponents. If b does not equal 1, if b to the x then is equal to b to the y, then x equals y. All right, let's throw in some numbers here so you can see the truth of this. 2 to the x is equal to 2 to the 5. What's x equal to? 5. That's all that's saying. All right, 2 to the 4th equals 2 to the x. X is 4. What if it was 2 to the x minus 1? Then I set 4 equal to x minus 1, add 1 to both sides, and sure enough, x is equal to 5. That's all this is saying. You can set the exponents equal if the bases are identical in an equal situation, in an equation. All right, so now the point of this is if we can turn these into, manipulate these numbers to have the same base, boom, we can set the exponents equal and we can solve the equation. So here, 32, well, it's not 4 to the anything, but 32 is 2 to the something, and 4 is 2 to the something. So I change that. 4 is 2 to the 2. So now I have 2 to the 2 to the x. And 32 is 2 to the 5. So now I have 2 to the 2x, and it's equal to 2 to the 5. So I can now set these two equal. 2x equals 5. Divide by 2. And I get x equals 5 halves. I've now solved my equation. Okay? All right, example 4b, solve. 25 to the x is equal to 1 over 125. Well, I first need to get this up here before I can do anything, because there's never going to equal, the bases aren't going to ever equal like this. So I bring this up as a 5 to the negative 3. 125 is 5 to the third. I bring it up, it becomes negative 3. Now they have the same base. I can set the two exponents equal. I get 2x equals negative 3. Divide by 2. I get x equals negative 3 halves. Okay, so if the number one of the numbers you're working with is in the denominator, use a negative exponent to bring it out. All right, so this is a long one. Okay, so 2 pi, solve for I. Okay, t equals 2 pi square root I over, you know what, that might be an L. I bet that's an L. That's why I always write my L's as scripts, because they can't be mistaken for I's. All right, so what I'm going to do is I have to isolate that. So first I have to isolate the radical. So I'm going to divide off the 2 pi. That's going to get me t over 2 pi, and I still have my radical. Well, now I raise both sides to the 2, and that gives me t squared over 4 pi squared. Well, now I have my L over G outside of the radical. So I multiply both sides by G, and I get t squared G over 4 pi squared. Now this has been solved for L. All right, using that equation, find the length that was L, because there's my L. Find the length of a pendulum. So I'm looking for L. There we go, so we can see it better. Well, the period of 3 seconds. Okay, that's my T. T is period, L is length, and they give me my G. So I plug those all into my equation. Most of this I can simplify. Notice I have seconds squared over seconds squared, so those disappear. I now have feet. 9 times 8, because the 4 crossed out with the 32 to give me an 8. 9 times 8 is 72. This pi squared is left in my denominator, and I'm left with feet. Okay, so the length is, if I plug all of this in my calculator, 7.30 feet. And that's my answer. Okay, and that's the end of today's lesson.